Hello everyone, welcome back to the Coding Game channel. In this video, we're gonna have a look at 3 more problems from the European qualifiers for the World Championships of Programming. If you haven't seen it, I recommend watching first the video I made last week about this competition because I explained the rules and the 3 problems that I solved were a bit easier than today's. So let's get started. The first problem we are gonna solve today is called boundary, and it's about tiling a bathroom. The examples actually tell us everything we need to know about this problem. So here we are only interested in the boundary of the bathroom. We have to put tiles on the floor. So the blue tiles is what we are interested in. The tiles have a width of always 1, and we want to know which possible lengths of blue tile are possible to cover the entire boundary without having to cut any tiles. So in the case of a 3x5 bathroom, we can find valid configurations with tiles of size 1, 2, and 3, as you can see in the examples, but not any other values. The test case of the 3x5 is actually present in the sample inputs, and the corresponding output is 1, 2, 3. The first value here, the 3, is just the number of values that are valid. A 12x12 bathroom would have 3 possible values as well. It would be 1, 2, and 11. We can find configurations of the edge of the bathroom with 1x1, 1x2, and 1x11 tiles, but that's it. And apparently we also should be able to process very large bathrooms, and in this case, well, there's only 2 values, but this will be maybe a performance issue as well. In that exercise, we can notice that there are only 5 different cases that we can have. By processing those 5 different cases, we should get the answer. So I've drawn the bathroom. Well, actually, we're not interested in the center. And for each corner, we can notice that there's always going to be a boundary between 2 tiles, either here or here. What this means is we'll only have a few different configurations for which we have to check the possible length. So for example, if I take this configuration, it means that whatever the tile length I choose, it will need to be a divisor of this length and also this length. The other 2 are actually equal to the opposites, so it's fine. But it means that A will be a divisor of here H for that value on the left, and also A will be a divisor of W minus 2 because it's the width of the group on the top. One other possibility will be this one, which we actually saw in the example. A will need to divide W minus 1 and H minus 1. And there's also a third configuration, which is this one. So here it's H minus 1 here for those 2 groups, and also W minus 2 for the top one, and W entirely for the bottom group. So here we actually have 3 different values that the tile length A has to divide. Okay, so I've drawn templates for the 5 possible cases, and so let's fill them in. The first case is the one I showed you first. We also have the symmetrical, so I'll put them next to each other. We have this one as well, which has its symmetry as well. And the last one has no symmetry because it's the W minus 1, H minus 1. What these drawings mean, for example, for this one, is that we have several groups of different lengths, and the length of the tile we choose has to divide all of these lengths. So for example, this one has to divide W minus 1, which is this group, and this group as well, has to divide H minus 2 here, and H, which is this group. And if we find all the values that divide all of those 3 numbers, well, it means that this value can be picked to fit this configuration. And we'll just have to take the union of all different values for those 5 cases, and that will give us the answer. I'll use the CoderPad sandbox so I don't have to install anything, and also because it has the default installation of Python 3.10, which is a similar environment to the one of the competition, with no additional packages installed. So again, the input contains multiple test cases. So here we will have the first line containing the number of test cases, and then we will have 2 numbers for each test case given on a line, and those are the W and the H. So let's parse those first. W and H are two inputs that are given on the same line. Then we're gonna need a function that finds all the divisors of a given number. Here we can do that with a simple algorithm that checks all the potential divisors between 1 and the square root of the number. This will be fast enough because the square root of 10 to the power 9 is actually less than 50,000, so it should be fast enough for our code. So here I'll implement a function that gets the divisors of a number n. The list of divisors is empty at first, and then I range from 0 to the square root of n plus 1. And if that number, so if n modulo I is actually 0, we'll add to the list of divisors I and n divided by I, and we can simply return the divisors here. Then I need another function that will return the numbers that divide all numbers provided in the argument. So we can do some magic with sets in Python, which can be intersected, so we can keep only the elements in common. So I'll define the divisors as the set of the divisors of the first number provided, and then for each additional number provided, so starting at index 1, I'll narrow down the set of divisors which are common to all of our numbers. So here I can compute the intersection with the built-in function, and then we can return the divisors here. Now we need to check the 5 different cases I've showed you. So let's check. The first one will be h and w minus 2. So I'll define a result that will be a set, and the solution to the problem will be all the numbers that are valid for at least one of those 5 test cases. So here I can do a union of the sets. So we had h and w minus 2, we need h minus 2 and w, which is the symmetrical test case. Then we need w minus 2, h minus 1 and w, and the symmetrical, of course, h minus 2, w minus 1 and h. And for the last test case, it's h minus 1, w minus 1. Okay, well, that's an ugly block of text. Maybe you shouldn't do that in real world code, but this is competitive programming, it's a special word. So the output format will be, we print the number of valid values of A, then k integers, so all the values that are in our results set. And they say also it has to be sorted from smallest to largest. So we can simply print the length of the result, then all the values in the results, but we have to sort them first, so sort it here. So let's run this. So the first test case is 3 and 5, returns 3, 1, 2, 3, it should be good, okay. Then 12 and 12 gives 1, 2, 11, let's check. Okay, perfect. And the last one gives us 1 and 2, which is good as well with the samples. Actually, during this competition, most teams got that exercise correct, but most of them also got that in 2 tries, because in the first try, almost everyone, including me, forgot this weird test case, which corresponds to the 2 on the middle right here. The second problem is called ice cream shop. It's problem D from this year. This one was solved by around half of the teams in the contest. There were many different solutions, but this one involved a lot of tricky special cases and tedious implementation, so it wasn't easy to get on the first try. So it tells us that we are on a one-dimensional beach with some huts in a perfect line, and they are all spaced by 100 meters. Each hut has some amount of people in it, and there's also ice cream sellers. When they want an ice cream, the people who are in the huts go towards the closest ice cream shop there is to their hut. And the problem is that we want to find the perfect spot to open our own ice cream shop. In this example, we have 3 huts with 2, 5 and 6 people in it. There's also an ice cream shop that's between the last 2 huts. And here, if we place our ice cream shop at the spot that's marked in orange, there will be 7 people coming towards us. And that will be the maximum amount of people that we can have towards our shop over all possible positions of our shop. For this test case, the perfect spot is in orange as well. There are 15 people here who would be closest to our shop in orange than to any existing shop which is in blue. The goal here is not necessarily to find the position at which we can place our shop. It's actually to find the maximum amount of people that we can find, but the algorithm would be exactly the same. So let's draw the axis. We have the huts that are spaced 100 meters apart. For now, we won't really care about how many people are in the huts. We also have ice cream shops that I will represent as small houses. Let's say we have a shop here and another here. Two are very close to each other. And the last one at the very edge of the beach. One thing to notice is that if we place our shop, for example, on that spot, we are only ever gonna see people who are coming from the segment between the previous and the next shop. We can also prove that for any given segment between two shops, the area of influence of our ice cream shop will be half of the length of the segment. So here, let's say I have 280 units in size. The area of influence, which is at the halfway point between our shop and the shop on the right, and the halfway point between our shop and the shop on the left. Here, this will be 140 all the time. So what this means is for each segment, we will consider all consecutive segments of huts which have a length of the space between the two neighboring ice cream shops divided by 2. So in that case, a segment of 140 units, which will be the area of influence of our shop. It can cover 2 huts because huts are spaced by 100 units. So we need to consider all pairs of consecutive huts like this. For the edges, it's a bit different because, well, here we could place our shop just here, for example, just to the left of the leftmost shop, and we can get all the huts that are in that direction, and the same for this one. Well, here we have no huts in that direction. This will be a special case in the code, which we may not necessarily want. So one thing I did was to create another hut at position plus infinity and another one at minus infinity here. And in that case, we can consider this segment as a real segment. And since the distance between those is infinite, we will have the area of influence as large as we need. Now there is another performance issue that we need to consider. It's related to computing all the possible areas of influence between two ice cream shops. So let's say I have another beach and we have two ice cream shops that are very far apart. The first possible area of influence that we could have is this one. So we need to sum the amount of people that's present in each hut in this segment. There will also be this possibility as well, this one, and finally this one. In that case, it will be quite fast to compute, but if we have 100,000 segments in a row to compute, it will actually exceed the time limit if we compute it naively. One thing we can notice when going from this segment to this one is that we don't have to recompute the whole sum. We can use something called a sliding window, which is actually a quite visual representation of what's happening. Here, to go from the first sum to the second one, we only have to subtract the number of people in this hut and add the number of people in that one. So instead of computing the entire sum every time, now we only have to subtract and add one value. So the algorithm of the sum will go from ON to O of 1. So the complexity will actually go from linear time to constant time. That's it for this problem. I won't show you the implementation because I don't think it's very interesting. It's very tedious, so I want to keep this video quite short, and it's already pretty long. The last problem I want to show in the European Programming Championships is this one. It's called Circular Maze, and you can already guess what's happening just looking at those two images. We are given a description of one maze like this, and we have to determine whether or not there is a path that goes from the outside to the center. In this case, for example, where I could just go around here and solve the maze like this. But in the second case, the path that we took, it's almost the same, but here we will be blocked by vertical segment, and there's actually no way to join the inside and the outside. This can look a bit complex, but actually there are a few things that make the problem much easier. So the formal description of a maze like this is that we'll be given n walls, and the walls can either be circular, so portions of a circle of a certain radius, and there are two angles delimiting the beginning and the finishing radius, which will give us the opening. And there also are straight walls which have a direction, and there's also the radius where it starts and the radius where it stops from the center. Okay, let's draw the first sample test case. It contains 5 walls in total. The first one is a circular wall of radius 1 and it goes from angle 180 to angle 90. So what this means, let's draw, for example, this point will be the center. The top direction will be 0 degrees, so it's a bit like the north on a compass. So it will go radius 1, so quite close to the center, from 180 all the way around to 90 degrees. Second wall will be radius 5 from 250 to 230. So where's 250? Let's say it's about here. From 250 to 230. Let's say it's about 20 degrees opening right here. Third wall will have radius 10 from 150 to 140. And the last, well, I won't be able to keep the scale, but it's from 185 to 180. So the opening will be just to the left of the south, let's say. And we have one straight wall from radius 1 to radius 20, and it's at angle 180. So it will be in this direction, and it will go actually from that circle, radius 1, to radius 20 right here. And you can see this actually corresponds to the first maze that we solved in the example. We can draw the path here, and that's the solution. So this one, it's possible to find a path between the outside and the center of the maze. So now, how do we solve this? There is one thing that will be extremely helpful. It's the constraints. Here we can see that the coordinates of each wall is an integer. So it means that, for example, there are only 360 different angles possible. And also the radius is an integer and it's between 1 and 20. This means that there are only 20 different possible values for the radius of a circular wall or a straight wall. What this means, it's that there's always going to be a limited number of possibilities for the positions of the walls and for the radius as well. So now we can still draw, for example, the first wall we had in the previous test case, and it will always match, a white line on my drawing and stop at 2 intersections. Now, instead of considering our maze as just a drawing, we can consider it as actually a grid of cells, because each cell will have 4 neighbors, or maybe less if they're at the edge of the maze. But that's it. If there's a wall present at that edge, it's quite easy to determine. If there's a wall, for example, here, it means that we cannot pass from this cell to this one. Otherwise, we can. And then it's just a matter of determining whether or not we can go from this cell to any of the cells in the center of the grid. And then it's just a matter of determining whether there's a path from the outside, which can be considered as a single cell, and any cell on the inside. First, I will want to generate a graph that tells me for each cell which are its neighbors that we are allowed to travel to. So we'll create a dictionary. The keys are actually a tuple of 2 values, which are the radius and the angle. So first, there are 2 neighbors on the graph, which are the cells immediately clockwise and counterclockwise to it at the same radius. For example, for this cell, it will be those 2 neighbors. We need to take modulo 360 because the counterclockwise neighbor of angle 0, it will not be -1, it will be, of course, 359. Now we need to define the neighbors directly to the outside and the inside of the cell. Here we will run sometimes into some special cases, which means in the center, well, the center cell will only have a neighbor to the outside, and the outside cell, so I've considered radius 21 here, it will only have a neighbor to the inside. So those are the 2 outside and inside neighbors defined. Then we need to transform the graph to remove the edges where there are walls between the cells. So we will need to parse the input. There's always 4 values in a wall, so it's type. Then there are 3 values that mean different things depending on if you have a circular wall or a straight wall. So if the type is a circular wall, the ABC values will be the radius and then the 2 angles that we can call T1 and T2 for theta. And of course, we have to convert them to ints. Then we can iterate over all the theta values of the wall and remove the corresponding edge between the two cells on each side of the wall. So I'll initialize the theta value, and then I'll just do a while loop. It will make it a bit easier for computation instead of using a range. So while we haven't reached the end first, so T2, we can say that the cell 1 that's on one side of the wall will be the radius of the wall and TH, which is the current angle, and the second cell is the radius -1 and TH. Now we can take neighbors of the cell 1 and remove the cell 2 and do the symmetrical, because cell 2 isn't a neighbor of cell 1 anymore. And then we'll increment TH by 1 and take the modulo 360 just in case we pass the 0-degree angle. Otherwise, well, we have a straight wall, so the type will be C. Here we have R1, R2 and the angle, which are provided in ABC. Here it will be a bit easier because we can just take the range between R1 and R2. We don't have to do any funky stuff with the modulo since the radius doesn't wrap around. Cell 1 will be again the radius and the angle that's provided. And the second cell, here we have to do some of the weird operations with the circle. It will be the radius as a first argument, and the other one will be the angle -1 modulo 360 again. Then we can remove each cell from the neighboring of the other, and this will give us the final graph. One last thing we need to do to solve this problem is to determine whether there's actually a path from the center to the edge. And to do that, there's actually a simple algorithm we can use on a grid graph, which is called a BFS, breadth first search. I'll not get into that because, well, teams have those kind of basic algorithms available during the contest. You can read the code here. It's a very simple BFS, and then we can wrap it up by checking whether there's a path from an outside node to an inside node. So the reachable nodes, I'll call a BFS on, I'll give it the graph, and then the node from which I want to start. This will be node 0, 0, for example, so that's any node in the center. And I want to check whether there's a node on the outside. So here I've specified my graph to go all the way to radius 21, which means that there will be no walls. And since there's no walls between the radius 20 and 21, actually all the cells in the outer layer at radius 21 will be connected to each other. So it doesn't really matter which one we pick. So let's say if 21 at angle 0 is in the reachable nodes, then we'll print yes, and otherwise we'll print no. Let's run this code to make sure it works. Okay, so this is giving me a yes for the first test case, which is actually what we're expecting. There are no apparent bugs, so we could submit that to the contest platform and hopefully get one more point on the leaderboard. In total, in the last 2 videos, we've seen how to solve 6 of the 12 problems of the Coding European Championships. Doing this in the actual contest would be very good. It would be enough to put you around 20th place on the leaderboard. So I hope you enjoyed the way of solving these problems. I found them very interesting. And if you find other ways to solve them, let me know in the comments, especially for the problem of ice cream and of the maze, which had many different ways of being solved. Thank you for watching until the end, and I'll see you in the next video. Bye!